My name's Troy Van Voris. I'm a professor of chemistry. I'm also the department head of chemistry, and wearing that hat, I want to express how excited our department is to be part of CUMIT and to be interacting with, just across the different disciplines at MIT. I'm also scientifically interested here. You might actually be curious why a chemist would be up here moderating a panel like this. I guess I should let you know that my research area up until recently was an area known as quantum chemistry. We're on the market for a new name. What we did was we used classical hardware and algorithms to simulate quantum phenomenon in chemical systems. And so the launch of CUMIT is really right up my alley in terms of the things that I'm interested in, because it's been a dream of mine to try to understand the quantum mechanics of molecules and materials for many, many years. And it's my pleasure to introduce our panelists. So we are going to talk about the future of quantum. And so we have some of the youngest members of our faculty right here to talk about what the future is going to look like, because they're going to get us there. So first to my left here is Harry Zhu. Harry is an incoming faculty member in EECS, so he'll be starting in March. He's not moving far. He's currently a postdoc at Harvard. And his interests are in fault tolerance and error correction in quantum computing. And he also, though MIT is not new to him, he was also an undergraduate here at MIT, so he knows the MIT culture. Next to Harry, we have Anand. Anand is the ITT Associate Professor of EECS, and one of his key research interests is in complexity theory of quantum algorithms. And he also has a long-standing MIT connection in that he got his PhD here at MIT with Aram Harrow, who we just heard about a moment ago. And furthest to my left is Soonwon Choi, who is the Weisskopf Assistant Professor of Physics. And he does not have a preceding MIT connection, but we won't hold that up against him. And Soonwon has interests in the non-equilibrium properties of quantum systems and also in the theories of quantum measurement. So why don't you join me in welcoming our panelists here. And first, I thought I would just give you each an opportunity to tell the audience a little bit about yourselves and what really interests you most about quantum.
Yeah, thank you. It's great to be back at MIT and joining this very fantastic kickoff for CUMIT. So as Troy mentioned, I work primarily on quantum architecture design and research, specifically thinking about fault-tolerant architectures. So I did my PhD at Harvard. Currently, I'm actually primarily at Quera Computing, the startup that was mentioned earlier, but also staying connected with the Harvard research community through like an affiliation. And I'm mostly interested in thinking about, with a lot of these advances that we've seen, both some of the nice theory and experimental advances we heard earlier from Jay and Hartmut, but also the technologies that have been blossoming in all kinds of different platforms. There's neutral atoms, trapped ions, superconducting qubits, and there's honestly been a lot of fantastic experimental progress and theoretical progress that motivates us to think, how should we design fault-tolerant quantum computer architectures to really get us to the places that we want to go with these systems, hopefully eventually getting to useful quantum computers. So that's the main area that I'm interested in.
Anand?
Oh yeah, so I guess I'm in the theory of computation group right now in the computer science department. So I actually started out as a physicist, as an undergrad, I majored in physics and then was in the physics department. But I guess now I'm in the computer science department, and I do feel these areas are kind of related, though. Like I was really interested in theoretical physics, like things like quantum gravity and so on as an undergraduate, and then I drifted over to quantum information. I think because you can view both theoretical computer science and say like theoretical physics as trying to understand sort of what is fundamentally possible in the universe we live in. And in computer science, like really the question is like, what is possible in terms of what can be efficiently computed by computing machines in our physical world? And I think the very beautiful thing about quantum computing is that people have proposed many different types of computers. They all seem to behave sort of the same in terms of the fundamental computational power, but not so for quantum computing. Like quantum computing seems to be fundamentally different from any classical computer architecture and working on exactly how it's different, in what ways it's different. It's just like a very exciting, subtle story. It's told us things about the foundations of quantum mechanics as well, I think, or like ideas from there have come into quantum computing, and this is what really inspires me and attracts me to this field.
Nice to meet you. I wasn't at MIT before joining here as a faculty, but except that I actually applied to MIT undergrad and got rejected, of course, twice. So I'm very happy that I finally got into MIT. So thank you. So I'm in the Department of Physics. My research program is generally half and half. Half is basic science in physics. Especially, I try to understand how statistical physics and quantum physics can be made compatible with one another. And turns out the best way to answer those questions is using the language of quantum informations. On the other hand, my other half of the research is coming up with the useful applications of quantum technologies, performing better measurements or better simulation methods, utilizing physical phenomena. But honestly, even though I sometimes say I have a two research program, I view them as exactly the same thing. There's one thing, which is just better understanding how to manipulate and control and of like many particle systems, they behave collectively. So I think in some sense, doing basic research in physics and like driving applications, this notion of quantum information is so central. So that's why I'm very excited about this effort.
Yeah. Thank you. Well, so we're here to talk about the future of quantum, and so it's a good day to dream big, and so I'd be interested for each of you to share with the audience, in your wildest dreams, what are you most excited about seeing emerge from quantum in the future? Maybe we'll start at the other end with you, Soon-Won.
Yeah, so I'm totally biased because I'm totally excited about the research that I'm pursuing at the moment, since a couple of years ago. So we recently put out an idea together with Professor Ike Chuang about how to combine quantum sensing and quantum computing. The idea is quantum sensing, we have an idea of how to use quantum mechanical effects like entanglement to improve sensitivities. But we are going further than that. Okay, let's integrate quantum sensors together with the quantum computers so that you not only improve the sensitivity, but process the data in real time, quantumly. And turns out for a specific example that we believe that's very versatile and widely useful, there's an advantage, a computational advantage of solving that problem. So I'm very excited about seeing that be realized in the real world. For example, perhaps we can detect gravitational wave better, or maybe we can develop NMR, the next generation of quantum computing enhanced NMR. Or those kind of practical applications, especially for the basic science, is something that I'm at the moment most excited about.
Great.
I guess maybe there are two things on a more sort of intermediate near-term time frame. I guess we'll hear maybe later in this panel about, there's a lot of progress going on in terms of building quantum hardware right now. And I guess from my point of view as a theorist, one phenomenon in theoretical computer science that's really, really cool, has paid off a lot for us, is the fact that there are problems that are hard to solve but are easy to verify. This shows up everywhere. This is sort of the whole idea behind the P versus NP problem, if you've heard of that. And this could apply to quantum computers as well, and that there could be tasks that a quantum computer can solve that you couldn't solve yourself with the classical computer, but you could verify the solution. We actually have examples, for instance, like Peter Shor's famous factoring algorithm does exactly such a task, right? It factors a number. We don't think you can do that on a classical computer, but it's very easy to check the answer by multiplying the factors. So I think one thing I'm excited for is when there are other examples of tasks like this with slightly more intricate notions of checking. I'd be very excited for when someone actually does an experiment that sort of conclusively we can check with a classical computer that the results are correct, and we're really confident you can't simulate them classically. I think there's been progress towards this. There's been partial results. It's not 100% conclusive yet, and I think that will happen probably in the next decade or so. So that'll be very exciting. And then in the longer run, I think complexity theory is all about understanding the landscape of what problems are easy, what problems are hard, what resources are needed. And really there's just a lot of potential for big surprises from quantum computing. Like if you look at the space of quantum algorithms, like there's, there was like an idea due to Oded Regev that originated in cryptography, like I guess 20 years ago maybe, and that's been very slowly converted into algorithms that might achieve speedups for some optimization problems. But that's something that is a very active story as of this year. Like so there's new developments happening. There could be huge surprises. We could just get a better understanding of complexity theory from quantum computing, and I'd love to see that happen.
Yeah, I certainly second Anand's last point about the hope for also new surprises and things that we haven't anticipated so far. I think for me, being in the field, certainly things like these decoded quantum interferometry ideas were quite surprising and kind of opening up new classes of things. In terms of things that I feel like are a little bit more well-established, but I'm nonetheless very excited about. In my PhD, I was actually working more on many-body physics and trying to understand dynamics, actually with Soon Won together in grad school. And back in the day, one of the things that always was nagging me at the back of my head was whether a phenomena that we see on these noisy systems, whether it was actual physics or whether it was just like some artifact, like maybe just like the dephasing kind of causes certain signatures that looks very similar to what you want to see. And so that's actually a large part of my own personal motivation for thinking and working on quantum error correction, because then you can really have a much better guarantee of some sort, or at least being able to say a bit more that really what I'm seeing really is kind of the underlying physical phenomena. And so I'm also quite excited now that these systems are really starting to get into a regime of fault-tolerant systems, of designing and, more importantly, implementing simulations that hopefully can teach us new stuff, even just in many body physics, but hopefully also in application-relevant areas using these error-corrected systems.
Yeah, thanks. And so, as we're here at the launch of CUMIT, I guess one of the questions that comes to mind is, in what ways can CUMIT actually contribute to making these things a reality? Like, what are the special things about something like this group that wouldn't have just sort of happened on its own? And I mean, I can point one thing out, which is, I wouldn't be up on stage with two people from EECS and a physicist on a daily basis. So at least for me, I see sort of some of that sort of cross-disciplinary connection being sort of a good fertile ground for that kind of thing. So I don't know, I'll just throw it to Anand first on this one.
I guess, actually, I think I was going to say what you said, which is like actually the fact that, so if you go to like computer science conferences and you ask the computer scientists, what will the big applications of quantum computing be? Like many of them will, wave their hands and say, oh yeah, quantum chemistry, simulating, and then you ask them, do you actually know any chemistry? Like none of us know any chemistry, right? Like, the last time we opened a chemistry book was in high school. So, and we don't talk to chemists on a daily basis either. So it's clear that quantum chemistry is important, or in general that simulating physical systems with a quantum computer will be a very important use of quantum computers. But many of us who know about the algorithms don't know much about the physical systems. So it's important to bring us together, I think. Yeah.
Yeah, I think especially as one thinks about kind of eventually end-to-end applications, that becomes even more important, really identifying places where somebody like working in an industrial setting would actually care is something that is highly non-trivial and something that the community definitely should strive for. I think that also connects in some ways throughout the other layers as well. So for example, if there is some application but the hardware platforms may be doing things in a certain way is a lot easier than other ways. And we've seen developments in this in various different platforms of certain operations are a lot more parallel to do. This is also something that either purely on the architecture side or purely on the application side might be difficult to directly think about. And so working together across these different disciplines is very important.
Yeah. There's a lot of things I would like to talk about, but maybe I should trim it. So I do think quantum science and technology is extremely interdisciplinary field. So as one representative example, my colleague, a professor, Seth Lloyd, introduced himself as a quantum mechanical engineer because he's in the mechanical engineering, right? It's very interesting. Our panel is from a School of Science and School of Engineering. We know each other's research agenda. Actually, there's no boundary. It's hard to tell Anand what Anand is doing is engineering, what I do is science. Totally not true. In some sense, what I do is engineering, what Anand is doing is a complete science. there's no boundary. This field is like completely mixed, and that's kind of like intrinsic nature of, I think, the quantum science and technology. So with this CUMIT efforts, I'm extremely happy because finally at MIT, we have an entity to encapsulate this very broad spectrum of research and education activities under a single umbrella. So we have opportunity to talk to each other, exchange ideas. And as like also Anand and Harry talked about, one of the most important challenges of this field is that despite we know it has a tremendous transformative power to revolutionize our technologies, like in computing or sensing in wider range, it is also true that we do not know a single pinpoint of like this is the real applications of the field. And I do think the only way to figure out what exactly to do with this new technology is to have engineers and scientists talking together and figuring out, okay, this is exactly what we can enable by new technologies. So the fact that we have these new opportunities and coming at MIT is something that I'm very excited about.
Yeah. All right, so I will carefully word the following question, which is, what is an area that seems to have a large gap between the public perception and the experts' perceptions of where quantum is at? And in that particular area, what would be an accurate assessment with you as experts of the current state of the art? I'll throw that to you first.
Yeah, I guess one example of something like that might be, for example, we hear about the nice progress on hardware platforms with so and so many physical qubits, and we're now well into the hundreds. But from the public, they might think, oh, we have like 100 or so, or even more usable physical qubits. But that's quite far. Like if you look at the really cool demonstrations that we've seen, for example, from Google. We use a lot of these resources to make a single logical qubit. And that's kind of barely at the level where we're scratching by and being able to improve it. And so that's certainly a gap where the amount of resources that we would actually want to do these deeper computations is still quite some distance from maybe the headline numbers that you might naively see. Yeah. Of course, there's been a lot of progress being made. Like, for example, 2 or 3 years ago, we didn't even have something that was below threshold, and now we've seen that being demonstrated in multiple hardware platforms. And this is also a case where once you're below threshold, especially when you're sufficiently below threshold, then you're really riding this exponential. And so actually, in some ways, progress there might actually be also in the coming years happening faster than one might naively look at just from extrapolating physical numbers.
Very nice, yeah. Anand?
Oh yeah, I agree with that. Should I say the rocket ship thing?
Sure.
Okay, this is an analogy that I do not know who I got it. It's not mine at all. It might even be due to someone in the audience in this room, in which case apologies. But like the analogy is that you have to make sure what progress measure you're plotting actually makes sense. Like if you were kind of trying to plot like say progress towards like sending a person to the moon during the space race by just like plotting the maximum altitude reached by I don't know a vehicle, right? You know, over time, it would have looked like it was sort of stagnating at like, I don't know, 100 miles, no more than 100 miles, and suddenly it like goes up, right? Like, but that's sort of like the wrong. So it would look like there was no progress being made for a long time because that was not the right metric to look at. You should have been looking at, I don't know, like how big their rocket engines were. I don't actually know anything about aerospace, but in our setting, like there are different metrics, and it's sort of, as Harry said, like it's really almost like a phase transition that we want to happen. Like are we below the threshold or are we above the threshold? And by these metrics, it seems like there's a lot of like, you know, steady, maybe even faster progress than people were expecting. On the flip side to that, I do want to say, like in terms of things that are maybe misunderstood, like I feel like one hears often in terms of the final like algorithmic applications of quantum computers, like people sort of assume that like a quantum computer will be able to speed up many different kinds of, say, optimization problems, or like difficult intractable problems that can be solved, that people struggle with classically, or might even be able to speed up machine learning, you know, which is exciting because machine learning is everywhere. I think there is little evidence that this is directly true. Like I think it's clear that quantum computers have some fundamental, you know, massive speed ups in them for some problems at least, by the evidence of factoring and then maybe these other problems that we can see. But they're not going to you can't just plug one in and shove in your favorite, NP hard optimization problem and hope for anything really useful to come out, like anything that would counteract the slowdown in clock rate you get from using a quantum computer. So it's really important. We're still at the stage from the computing perspective of understanding just the basic science of like what can you do and what can you not do with these machines. It's not like we have an application in mind and we're just going to drop it in and it'll speed things up.
I cannot add too much because the two of you already spoke. But I do agree that there's I don't know whether there's a big gap actually in some sense. Like there's a huge hope and expectations about our community. On one hand, they are completely overestimating our current technologies, for example, or specific applications. Like as Anand said, it's not clear whether we are going to revolutionize a particular applications. And when the news articles quote on numbers, okay, some calculation they could have done, like certain number of years, we could have done in like certain number of minutes. It's not wrong, but it's very misleading. From that point of view, I think there's a large gap about what public, perceives our community. On the other hand, I think the public also underestimates the full power of what new technology can bring. Sometimes just because we don't know the boundary of the technology, we don't really know how rapidly things could change. So due to these like two gaps, one is overestimating or like overhyping our current technologies and the applications. The other one is underestimating the power of like basic technology or basic science, where they could actually revolutionize, the revolutions. In some sense, that's my assessment. So it's hard to say whether the gap is very large or small because it's more like a multidimensional problem. Yeah.
Mm-hmm. Well, and listening to all of you and thinking about how it can be so hard to assess progress. Looking ahead, what should we be, and that there's this phase transition that's coming. Looking ahead, what should we be looking for? What would be the headline that would make you say, aha, I saw that, now I see that phase transition is much nearer than it was, or maybe we have now crossed over it. Like, what are the things that we should be looking for that would be the news items that we'd say, aha, we're one step or two steps or a big step closer. I'll throw that one to you first, Soon. Since you have to go last.
I'm a very practical person, so I'll put my metric as usefulness. But don't get me wrong, my usefulness is not necessarily like money making. So it is true that already existing quantum devices, we are taking some measurements and doing experiments. And from those experiments, we learn about physics. So at the level, now it's like research in basic science. Because sometimes we do some experiment just for fun, and it leads to the results we never expected and not anticipated. And that leads to the more serious research. And turns out the same thing could have learned without quantum simulators. However, could we have really learned without quantum simulators, because we have not have done that type of experiment. So from that point of view, that's, in my view, like completely useful task, like this, inspiring the basic science and exploring the regimes that we never really thought about. But I want this usefulness metric to be, propagating and expanding. Not only within the physics community, maybe also in some other engineering communities, or even within the physics, maybe other areas, and eventually, outside of academic areas and then to the industry.
Yeah. I guess maybe some specific things. Like I guess if you're talking about like progress in actual hardware that we have and things we can run, like I think one thing I've liked a lot is this idea that I think Google has actually been sort of proposing, which, well, it pleases me as someone who's interested in verification of computational problems. So that's like a very high standard. Like, can you check by means of, say, an interactive proof or something that a computation was done correctly? But one thing they've said in their recent work is like, at a bare minimum, like you should be able to get the same answer if you run the same computation on a quantum computer with a different architecture, right? Like that's sort of like a minimum required for verification. And it was like, it's not clear, or I guess they have claimed that they have done a computation that could be verified in such a way, but I guess no one has verified it yet, to my understanding. So I think that is like a type of result for more and more complex problems that would give me more and more confidence that we're doing something interesting. Like if two very different devices show the same signal for something that we have no straightforward way of simulating classically, that would be very cool. I also do want to say, just as a theorist, like I want to say there's clear progress can happen in theoretical work that's like not related to like whether like a device is doing better or not, but can still tell us that we're closer to an application. So, for instance, like one story that has been proceeding for a long time is this question of constructing quantum money, which is like a very cool object, which kind of uses the fact that quantum information is fundamentally uncopyable to build like money that's in principle like impossible to forge. And there's been like a quest to sort of build this using weaker and weaker cryptographic assumptions, like what's called public key quantum money, like money that you can verify that a banknote is correct without knowing a secret key. And we don't know how to do it yet from a standard assumption, like a cryptographic assumption that everyone believes is actually secure. But people are making progress towards that. If someone discovers that, then I would count that as like major progress in quantum information science, even if we don't have like the quantum money states in our hand just yet because the hardware isn't there yet. So that type of work is also making a lot of progress, I'd say.
Yeah, maybe one more thing I'll add on top of like the verification is a lot of these tasks also tend to be a parameterized family. And so that once you're past a certain point of like kind of the task doesn't become trivialized just because of the small size, it does present a metric that you could at least somewhat use as a proxy, even if it's an imperfect proxy because of the details of all of the problems.
All right, thanks. Well, with a final question, I'm sure I'm the only person in the room who enjoys sci-fi, but I do. And in most sci-fi stories, the development of a quantum computer is actually a pretty bad thing. It's usually like one step away from the end of humanity when they develop the quantum computer. So that's one way to conceive of quantum computers, one step from the end of humanity. I'm guessing that's not how you each conceive of quantum technology. But I do want, I think it is useful for us as we're thinking about, the future of quantum. What should we think about quantum as being? Like, what is the metaphor with which you approach it? Do you think of it as a disruptive emerging technology and a driver for economic growth, a promising tool for investigation, some entirely new discipline that we're just, beginning to probe the edges of? How do you think about it? And I'll let you choose who soon want.
Yeah. So I thought about this question a bit, and then I think behind the scene, I think there could be some phase transition, like some rapid explosion of the field. But to public people, I think this technology may invade almost at the inevitability as a very smooth process. And I give this particular example. Like we talk about like energy, like we need some energy on a daily life. It's a part of our language, right? Not necessarily technology. But this concept of energy is such an abstract and sophisticated thing. So we cannot touch it. We cannot grab it. It's not a physical object. The fact that the energy is important physical quantity is actually a very highly advanced one. I imagine in the future, I don't know when, but in the future, people talk about entanglement like that. Oh, my phone is so bad, entanglement connections. Like, what's going on? Like, can I use like different technologies to have a secure connection? Like, oh, my phone, this transaction is so slow. Like this kind of things. So in my view, at some point, it'll be very transformative technology, but not in a disruptive way, or more like a smooth transition into the a new set of technology. So that's my view.
Yeah, I guess from my point of view, I agree with everything Suman said. I think one area where quantum could have in the near term a disruptive effect, we don't believe it will be massively disruptive, but we don't know for sure, is in cryptography. So we all know that quantum computing will make cryptography based on factoring insecure. So things like the RSA crypto system. Now there are candidates for replacements that people are fairly confident about, and there's steps being taken to put them in place. Like NIST is working very hard on this, on designing new standards and rolling them out, and we should be all ready. But I mean, who's to say another Shor is not going to come around and break one of those, right? So it's very important to think about that, I think, and to have as much evidence as possible that our cryptographing infrastructure is truly secure against quantum computers, because if we live in a world where there is no public key cryptography possible, I think that would be a very different world from the one we live in today. Like, that is what enables so much of what goes on the internet right now, so much of our communications infrastructure. So that's important. I mean, that is a unlikely but possible way that like quantum could have like a very disruptive effect, like in the near future, I would say.
Yeah, I guess for me, a large part of what makes it maybe interesting is also just the fact that it's, as Anand was mentioning at the beginning, it is a new computational regime that we didn't have access to before. And so in the same way that one might be interested in finding the Higgs boson as a fundamental science endeavor, and a fundamental science endeavor in which part of the process actually also leads to offshoot technologies like the internet or otherwise. I also view in some ways developing quantum technologies as a very similar front, where you're going into a regime where you know there's something different about it. And of course, from a fundamental science perspective, we'll be able to do something that, that we wouldn't be able to do otherwise, but it could also lead us to do other interesting things, or maybe perverse things in the case of cryptography. And I think both learning how to use those and also kind of being aware of these consequences would be very important.
Excellent. Well, why don't you please join me in thanking our panelists.